My name is Peter,
And my name is CJ.
and today we are going to talk about the Magnus effect and its application in soccer.
We're going to start by defining the Magnus effect.
Then we will talk about different physics concepts that are used to describe the phenomenon.
And finally, we will show different ways that the Magnus effect is seen in soccer.
We start by answering the question, what is the Magnus effect? The Magnus effect appears when a spinning body travels through a fluid and creates a difference of pressure on either side of itself, causing it to curve through the fluid and experience a force perpendicular to its motion. This effect can be further explained by Bernoulli's principle, which states that faster moving fluids exert lower pressure. There are a number of Physics 191 concepts that we can see to help explain the Magnus effect. Firstly, a combination of friction and drag explain that when the object is spinning, it drags air around it due to the friction. This generates a lift due to Bernoulli's principle, which is the force perpendicular to the motion that causes the object to curve. Secondly, the circular motion or centripetal force explains that a high and low pressure also result in the aforementioned force perpendicular to the velocity vector, and this we can recognize as centripetal acceleration or circular motion, which we can model based on Physics 191. Another important physics concept that we didn't touch on but helps explain the Magnus effect is Bernoulli's principle. Bernoulli's principle states that faster moving air results in lower pressure, causing lift. This is one of the fundamental reasons why planes fly. We can see in the Magnus effect example that the spinning object drags the air due to friction, like we said before, and this generates the lift due to Bernoulli's principle, causing the object to curve.
In this demonstration, we have a tennis ball spinning through the air. As shown, due to friction, air is wrapped around the ball. As more air is wrapped around the ball, it creates a downward force. But due to Newton's third law, there must be an equal and opposite force upwards. To calculate the Magnus force in newtons, we can use the following equation, where rho is equal to the fluid density in kilograms per meters cubed, v is equal to the velocity of the object in meters per second, omega is the angular velocity of the spinning object in radians per second, r is the radius of the object in meters, and a is the cross-sectional area of the object in meters squared. And just like any other force, this equation is equal to the mass of the spinning object in kilograms times the acceleration due to the Magnus force in meters per second squared. Now you might be wondering, where can we see the Magnus effect being used in soccer? The curve in soccer, often called bending the ball, is the result of the Magnus effect. When a player strikes the ball off center, it spins rapidly as it travels through the air. This spin creates differences in air pressure on either side of the ball, causing it to swirl in the direction of the spin. The ability to put curve on the ball has become an integral part of modern-day soccer. Many players use curve or in-swing on corner kicks, free kicks, or crosses. It provides a way to avoid defenders and trick goalkeepers. And since both of us played soccer for most of our lives, we decided to go to the field and test out the Magnus effect ourselves. Now let's slow these videos down and analyze the Magnus effect in more detail. As shown, after each kick, the ball is spinning sideways. Therefore, as the ball travels throughout the air, the ball curves.
In a soccer game, in an ideal scenario, the fluid density of the air stays constant, as does the radius and cross-sectional area of the soccer ball. This means that if someone wanted to increase the amount of curve due to Magnus force of their kick or cross, they would have to either increase the velocity of the ball by kicking it harder or create more spin to increase the angular velocity. In both of these scenarios, the Magnus force would increase, resulting in more curve. We'd now like to perform a simple Magnus force calculation using the equation we found earlier. First, we looked up the average air density in St. Louis, which was 1.23 kilograms per meter cubed. we plugged in an initial spin rate of 10 revolutions per second, or 62.83 radians per second, and an initial speed of 20 meters per second. The official soccer ball has a radius of 0.11 meters, which can come out to a cross-sectional area of 0.038 meters squared. When all of this is multiplied, we arrive at an answer of 6.46 newtons of Magnus force. We must note that this is initial Magnus force, as air resistance and gravity cause the ball to slow in both spin rate and speed. The Magnus force will therefore change. Another thing to note is that a more realistic equation for Magnus force would use a lift coefficient. However, since the lift coefficient is proportional to the spin rate, radius, and velocity, we were able to substitute in for the simpler equation, which we can do because we know the values for the soccer ball scenario.